All right. Waves. Let's keep going. We got a simple mathematical, simple algebra equation that is a little slippery when it comes to the physics. You really have to think about it. We're describing waves. Remember this equation. The wavelength, which is an emergent property, combine blue and red and you get purple, is in meters per cycle. Right? Remember that. Think of that in meters per cycle, or nanometers, or whatever you've got. It depends on the frequency of the wave and the velocity of the wave, which I showed you. If you vary the velocity, again, if you go faster, it's going to stretch the wave out. If you oscillate faster, you won't go very far before you complete a cycle. So faster, longer wavelength, faster oscillation or higher frequency, shorter wavelength. That should make sense. Okay, but do you see the delta x equals vt? Think of this as delta x, kind of, right? That's the v. And this is t. Well, frequency is 1 over the period, so there's your t. So remember that, just remind yourself, and again, do it over and over for a week or whatever, and make sure you own this. But the interesting thing here is the causality. So this comes from those two things happening, an oscillation that's traveling, a traveling oscillation. It's caused by these two. What determines the wave, the frequencies of the wave, is the frequency of the oscillating source. So I have to vibrate my throat to create the vibration in the sound, which will travel one thing to the another, translate, or propagate is the other word that we use. So that's easy, just whatever it is. If you have a radio wave, a radio antenna that's sending out a radio wave, its electrons oscillating, and the rate at which they oscillate will be the frequency that they send out. Okay? If you have a wave in a string, then it's my hand that's the source. Right? So there's some source, something's putting in energy or creating that oscillation. Fine. But what about that V wave? Well, we said the V wave is determined by the medium. Properties like what can I change? I mean, V wave, what does it depend on? It doesn't depend on that equation. Now, I mean, if you know the wavelength and you know the frequency, sure, you can solve for V wave algebraically. But what's determining the wave speed is not these guys. Okay? It's going to depend on something else. And the easiest thing to do is to think about string waves. So we're talking string waves for now. And light, well, that's a whole nother can of worms. Get into relativity and space-time and things like that. So, because the medium of light is space-time. So let's take a look at this. How can I change the speed of a wave? And I'm just going to do a little wave pulse. Right? It's clearly traveling from me down and back. It's reflecting. We'll talk about reflection a little bit. Okay, so I'm just doing a wave pulse. And let's see. What's happening? If this piece goes up, then it pulls the next piece. And when that goes up, it pulls the next piece, and that goes up. And there's a tension. If I have less tension, it snaps back more slowly. If I have more tension, it's going to snap back faster. So that tension, and if I were to do a force diagram on it, I'd say the tension is down into your right and down into your left. Right? Tension, tension. And then they have the two sideways would balance, and the downward would create that downward snap, that oscillation, right? So if I have more tension, it should pull it down faster. If that pulls that down faster, that's going to move this, move this, move this. And so, watch. If I have a low tension, it goes that speed. If I go a little more tension, pulling, it's faster. If I have more tension, much faster. So, all right, cool. Tension. Let me put that in here. If I have more tension, I have more velocity. So I'm going to put that over here as I'm going to write it as this for right now. Force tension in the string, or FT. Now, some books might use T. What's the problem with that? I got tension in newtons or pounds, the force. I got T for period, which is seconds per cycle. So I don't know. I kind of like FT. That's pretty good for me. So that's my preferred. I don't really like that. But you will see that. You just have to know the context, and there's no way around it. It's not wrong as long as you don't mix it up with a period. Fine. So there's more tension, more wave speed, less tension, goes slower. Let me show you that here. So this is kind of like that string, but the wave is going back and forth. We'll get into that a little more. Now what happens if I so I can adjust the tension with these guys here, and it has an effect here. Now you saw, wait a minute, you adjusted the tension, that affected the velocity, but the velocity affected the frequency. Doesn't that contradict? I want to preview this. No, there's something else going on called a standing wave. We're going to get to that. But you can adjust the tension here in your string. And it's pretty neat when we talk about resonance, standing waves, and we'll get to that too. But you can adjust the tension. That's one thing you can do. You can also adjust, notice that these are a little less massive. So you have some strings up here that are thicker, wound with metal here, nylon down here, and they get thinner and thinner. So what difference would that make? Suppose I have more mass. Well, what do you mean mass? Mass of a piece? No, I mean more mass per length. More mass per length. Well, let's see, the tension's snapping it back, but if that piece has more mass per length, it's going to have more inertia. And so it should make some sense, without doing that force analysis, you can do it, that if I have more mass per length of string, then it should be a slower wave, more inertia. Well, that's kind of like the pendulum, remember that? Okay, cool. Except the pendulum, the mass didn't matter, did it? Why not? Because gravity, in that case, is the only player. So gravity increases with mass, and inertia increases with mass. So gravity is a special thing. When it's only gravity, the dual role of mass goes away. But if it's other forces, this force doesn't, it's not because of gravity. And so mass does matter here. Right? So the pendulum, yeah, the mass went out. But here, the mass is there. On a spring, the mass stayed there. More inertia on a spring makes a slower oscillation. Okay, so this kind of makes sense, but let me check my units. I always check my units, because that's what I'm getting to know, just getting to know you. Okay, that's equal to a Newton. I'm going to use SI, so that's a kilogram meter per second, like MA, but we know MA is not a force, divided by mass, which is kilogram, per length, which is M. All right, cool. Wait a minute, kilogram meter per, that's meter per second squared, isn't it? Force is in kilogram, mass times, okay, that looks good. And this is mass per length. Does that look good? All right, cool. Let's do that. All right, and then that's checking those units. What do I get? Well, I get, wait, do the masses cancel? How do I do that? How do I do that algebra? Multiply times M, multiply times M. Do to the top what you do to the bottom. That got rid of that. Now the kilograms clearly go away. So this is meters squared per second squared. Wait a minute, that's wrong. I have a solution. Let's just take the square root. Now, maybe there's a 2 in here that's missing. Maybe there's 1/2. Maybe there's a third. Maybe there's a pi. Something like that. No, in fact, this is the right equation. And how do I get that right equation? Well, again, and you can do this or look it up in a text. I'm not going to go ahead and do it for you. I take a a string and I stretch the string so that it goes like this. I look at one piece and I say, hey, there's a tension there and there's a tension there, so that I've got a component downward and a component downward. And that's what's snapping it back, and I treat that very much like a spring, right? Like an oscillation due to a spring. And you get, in fact, that. So the units got you close. They didn't tell you that it was definitely right. Maybe there was a factor missing. This will get you that derivation. Now what about air? Well, it's the square root of something like tension and something like density. We talk about the bulk modulus and things like that. So you can look that up too. And the speed of sound in air at standard pressure and temperature is about 343 meters per second. If you want to roughly think of that as 700 miles an hour. Where does it come from? Well, it depends on things like temperature, pressure, water content, density, and things like that. Okay, cool. So this should make some intuitive sense. You've got different strings on a guitar having different density. You've got the tension being adjusted here. But they go back and forth and something interesting happens. We're getting there. We're going to get to that too. And I think, oh, one more thing. I wanted to note what books will write for this guy here, mass per length. That's problematic too, because often we'll use lambda as mass per length. Well, that's really a problem, right? So some books will write mu, right? The Greek letter mu, or mu is anglicized. And then so, sometimes you do that and then all of a sudden you switch gears. Well, you have, they got the T, and what are you going to do? And that's just the way it is. So know what it means. Or just call it mass per length. Or maybe you're going to do, I kind of like M per L, the string. Take a certain length, get the mass, stick it in there. Anyway, get the physics of it, and you realize then that the tension in a string and the mass per length, more mass per length slower, more tension faster. Determine that. Given one string, you can oscillate it at a high frequency or a low frequency. It's the combination that gives you the wavelength. Okay? You can't adjust this. Okay? So we're going to get into some interesting things that I've kind of hinted at, but this is a very good foundation. And I think we're good to go. So you have that causality. Make sure you remember that. And we're going to now talk about some phenomena, descriptively some, and then we'll go eventually get to our mathematical description. So that's it.